To have you all here. Great. Welcome, everyone. Welcome to our Openscapes community call. We are recording this call to share on YouTube and with other colleagues. And there's a transcript available. I'm Julie Lowndes. I'm the director of Openscapes, and Openscapes is an open source approach and movement that helps researchers and those supporting research to find each other and feel empowered to conduct data-intensive science. We're really excited that you're here at this community call to share our partners and community work in progress. All Openscapes activities are bound by our code of conduct. And there's a link in the Google Doc that is in the chat. A few guidelines are to be respectful and value each other's ideas, styles, and viewpoints, and to lead by example and match your actions with your words. If you need any help or have questions, please message Zoom hosts, myself, Julie Lowndes, and Steph Butland. Our plan for today is that we're going to be sharing about what we're learning about cloud costs for earth science workflows in our JupyterHubs. The format of today's call we'll have several stories and demos from this really cross-cutting collaboration between open source infrastructure, government agencies, and science communities. We'll have 10 minutes for discussion at the end. And as you have questions throughout the call, you're welcome to use chat, you're welcome to use the doc, and then we'll have a time at the end of the call for a broader discussion after we've had the demos and speakers. So please feel free to contribute. We have really fantastic speakers in today's call. We have Tasha Snow, who's a co-founder of CryoCloud, and Tasha's just given a wave. Their full bios are in the doc, so you'll be able to read more about them also. Tasha Snow, co-founder of CryoCloud. Andy Teucher is a core Openscapes team member and software developer. Eli Holmes is currently the lead of NOAA Fisheries Open Science. Yuvi is co-founder and tech lead of 2i2c. Alex Lewandowski is a research software engineer at the Alaska Satellite Facility. So these folks are going to share what we're learning about JupyterHub cloud cost and usage, and really excited that you're all here. So thanks so much for being here. And I will pass it over to Tasha.
Well, thank you, Julie. Can you hear me and see my screen?
Yes, we can.
Great. Just to give us a quick overview of why we, are here talking about JupyterHubs and why they're important for research. This is what a JupyterHub looks like in general. We have notebooks on the right. You've got your file system on the left. You can plug and play and have a lot of different kinds of tools in here, including things like RStudio or MATLAB. You can have a remote desktop. You can pretty much do everything you would do on your laptop. But it's all fit into this Jupyter Lab looking tool called the JupyterHub. And the reason why it's so good for research is that the Jupyter ecosystem is super flexible, it's modular, and it's fully interoperable tooling. So if tools are built that can be used in Jupyter, they can all be interoperable with each other and plug and play. And so no matter where you're using this JupyterHub, you can use it from different kinds of laptops, and in the cloud, not in the cloud, different kinds of systems. You can use all different kinds of data and different kinds of tooling. It's all agnostic to that, and it can be used all together, and it also facilitates collaboration. So it's really helpful for serving a range of communities, and you'll see that in the talks you'll hear from today from our different communities. So Openscapes is serving these communities to help improve technical skill building, teamwork, and collaborative community development. CryoCloud is meant to support geoscience research, training, and collaboration in the cloud. And Open Science Lab is meant to provide access to SAR data and processing in the cloud. And so we're really serving different kinds of users. We have different development structures, guardrails, and different amounts of storage and compute allowances. But having this JupyterHub ecosystem makes it super flexible to be able to support all of these different kinds of uses. And so we can build JupyterHub differently if we're teaching classes versus hack weeks and workshops. We can serve exploring science, exploratory science research. We can support workflow development, tool development, collaboration, and easily supporting sharing and publishing. And so JupyterHubs in general are different for a number of different reasons. They are still very difficult to deploy. They take a lot of expertise to do that, and we're still figuring out a lot of that, which is why we have the call. But in general, for our users, it's meant to enhance access. So for our users, all you need is some sort of computer and a little bit of internet, and you can access this. So it can help to bring science to other places in the world that may have been historically underserved. Also, with the right kinds of training and workflows available to users, we are able to get undergrads up and running on a NASA data store in an afternoon. You really accelerate how fast you can bring beginners to the state of the art with the right kinds of things in place with this sort of JupyterHub platform. We can also really enhance teaching of open science skills and sharing and publishing. So in statistics course taught at Berkeley, over the course of a semester, they do a research project and they build it into a Jupyter book. And because Jupyter book is seamlessly kind of integrated into JupyterHubs and labs, they can learn cloud skills and also build this Jupyter book to share their made paper, their analysis code, and like build tests. And it's immediately interoperable using my binder. So this really enhances open science, and they can build these hubs for teaching, supporting a couple thousand students in the cloud for $1 to $2 per student per semester. So it can be done very cheaply if it's built properly for this. And of course, the most important thing with research, it can accelerate science. So this is an example of my research workflow before working in the cloud, where I was processing Landsat thermal data to create sea surface temperatures. And so manually searching, downloading, and unzipping data, and then processing it and keeping all the intermediate steps. This was 6 terabytes of data storage and a weeks long pipeline, at least, if not months. And then now all of that gets condensed using a JupyterHub where we have access to cloud tools and data, and it's now orders of magnitude less processing time and data storage. So we can really reduce the time for iteration, time to solution, and improve impact. So that's kind of the background on JupyterHubs, and I'll turn it back to Julia.
Thanks so much for that overview, Tasha. And Andy Teucher is going to share next about communicating usage and costs.
Right. Can everybody see my screen? Look okay? All right, thanks. So yeah, at Openscapes we administer a few different hubs, and we've been trying to figure out how to sort of both understand and communicate the use of those hubs, and what those things are costing, both to help us understand and plan our programs, but also to help researchers understand how much their workflows are going to cost them as they move workflows into the cloud. So we are working with NASA and NOAA Fisheries to host JupyterHubs for them. We're working really closely. 2I2C provides the real expertise and the infrastructure for hosting these hubs, and so they're the expert. We've been learning a lot from them. We have sort of these 2 main hubs, one for NASA and one for NOAA. And these are really for scientists experimenting with cloud-based workflows, developing tutorials, developing workshops, and sort of figuring out how to use cloud data in their workflows, as well as teaching workshops. As I said, they're hosted with 2I2C, and all of our hubs are on AWS. And so I want to talk a little bit about sort of some of the typical costs and how we monitor those for like the base costs for running a hub, the costs for running a workshop in a JupyterHub, costs of data storage, and then a little bit later we'll talk about how costs of an example workflow might look. So there's a lot of different tools for monitoring cost and usage, and it can be a little bit overwhelming. 2i2c has this great suite of Grafana dashboards that we can use for real-time monitoring, really get into the depth of what's happening in the hubs. AWS has their Cost Explorer. These are costs that, the real costs that we're being billed for running the hubs. They're pretty high level. You have to log into the AWS console and see them. And so these like bits and pieces are really useful, but it's harder to sort of bring it together into an overarching view of what's happening. And so we've been working on some automated reporting, querying the backends of these services to sort of pull together some reports for the costs and the usage levels of the hubs. And so I've been working on an R package because that's what I like to do for monitoring for querying these data sets. We're calling the package JupyCost. It's sort of pretty early days, but it queries Grafana and it queries AWS Cost Explorer APIs to help us sort of drill down into specifics of how our hubs are being used and what those things are costing. So this is just a snapshot of what's in those reports. And they're hosted online and posted every month on the openscapes.cloud website, where we're sort of documenting how we administer and run these hubs. And I want to talk a little bit about, like I said, some of those examples of like what it costs a hub to do particular things. So just as an overview, this is the NASA Openscapes hub. We have an average of about 7 users per day. We've had 750 plus users log into the hub since its inception. It's been going for a couple of years. We have a lot of users who use the hub like rarely or sporadically, like maybe for one workshop or dipping in and out to test things out. And we have a few users who use it a lot. And so we have sort of like an interesting distribution of usage. About midway through 2024, 2i2c helped us stand up a workshop hub, specific hub that we're using for hosting workshops. So it has a much simplified authentication mechanism, so we can let in lots of workshop participants easily. And that's really been a game changer for us for hosting those workshops. And so you can see in this figure, these are the spikes of the number of users. Prior to the workshop hub being launched, we had these spikes in our regular hub. Those were workshops. And then when our workshop hub came in, you can see it took over, and these are the workshops that we've hosted in that hub, or that NASA mostly have hosted in that hub. And it's been really helpful. So that's sort of a context of like how we use the hub, the numbers of users, etc. And so when you're hosting one of these hubs, there is some sort of base level cost for having it just sit there at rest, even with no users logged in, because you have to have some infrastructure running all the time to sort of like hold your login page and spawn new users, etc., etc. And so that costs about $13 a day. And that's kind of fixed over time. It doesn't change too much. Running a workshop, obviously, we're going to have like an increased usage in the hub, and so you get these sort of spikes in costs. But as Tasha was saying, if you have things set up correctly, these things don't have to cost a lot. So this is an example of a workshop that was held in February in Italy by some NASA Openscapes mentors at the Biospace conference. There were about 30 users, and the cost was about $30 for a 2-hour workshop. So about $1 a user for the workshop. So really, really cost effective, and it allows it allows everyone to log into the same computing environment. There's no overhead in terms of setup, and it's a really, really effective way to get users and learners up and running quickly and easily.
1 more minute, Andy.
Okay, perfect. Thanks. And then data storage is one that we've struggled with a lot. Data storage in the cloud is very expensive, or can be if you don't sort of do it in the most optimal way. And this is an overview of the directories of users, the home directories of users in the hub. And so you can see we've got some sort of like heavy users, with hundreds of gigabytes of data storage, with a total amount of, or down to just over 1 terabyte now. But this accumulates, this data costs money just sitting there. And so, from January to today, this cost of the storage accumulates to about $600. And so there are alternatives such as object storage in AWS S3 that are much cheaper and more effective, but requires learning new workflows. So we're using them as these monitoring tools to help us sort of understand users' use and help them to shift to these sort of alternative methods of data storage. I think that's it. Sort of a brief overview of what we're doing to monitor the various aspects of cloud usage. And I'll turn it over to Eli, I believe. We're back to Julie.
Eli, great. Thanks, Andy.
Thanks. Yeah, and Steph, if you can share the slides for me. Or I can share if that's easier.
Give me a second.
I'm nearly there.
Yeah.
Okay.
Share. Oh, Julie, you're doing it. Thank you.
I got it.
Excellent. Yeah, can you put that into slide mode?
Yep.
Yeah. Excellent. Hi, everyone. I am Eli Holmes. I'm from NOAA Fisheries, and I'm the lead of NIMS Open Science. What does that mean? I'm leading an effort for a really big upskilling of our staff, our technical staff across all of our line office, so all of our organization, upskilling them in terms of their ability to be working with data, big data, integrating more types of data, and also migrating to more reproducible workflows, which means workflows that are scripting in nature. So we don't want to be like interacting with lots of disk squares and like poking at things or working with Excel files. We need people to migrate to scripting, but also really upgrade their skills. And as part of that, we are working with Openscapes and using JupyterHubs a lot, trying to understand how JupyterHubs can help our staff with this learning journey. And one of the big barriers that we have is, why don't you go to the next slide? Next slide. Yeah, back, yeah. Thanks. So a barrier that we have is a lot of our technical staff will be statisticians and fisheries modelers, and they'll be working in R. R has a really rich, powerful ecosystem of statistical tools. A lot of the cutting edge statistical packages are coming out on that. But they need to be interacting with these physical and biological oceanographers and working with big data. And the tools for that are much better in Python. Next slide. So I have been working on getting images. So I work on Docker images for our hubs. That's one of the big things I do. How do we get these two environments to work really well together? And if you're on one side or the other, like if you're in R, you probably think, oh, just use reticulate, it's fine. Well, I will tell you that the Python users will be like, you're kidding me, no. And on the Python users, they'll say, oh, just do conda install R. And the R users are like, are you insane? So like each side has these really powerful and rich environments. And I've been working the last 2 years with Luis and with Carl Bettiger, trying to get these images that work. And we came up with endless weird bugs. I mean, it's so hard to get these geospatial things to work. Next slide. So I've been working on something called PyRocket Docker image. And this is version 3. And this one actually kind of works. Next slide. And this, I took a different approach. I said, hey, let's let the communities who know how to develop these environments will have used their environments, and I will figure out how to install these separate environments that live separately. So in my image, it has the Pangeo kind of world. It's actually very similar to the CryoCloud image. And then for the R side, it's the rocker geospatial. And these worlds are kept separate, but then they can talk to each other. So if you're in the Jupyter lab, you can open up an R kernel, and it's not going into Conda. It is talking to the rocker geospatial. Everything works. If you are in the R side, you can use reticulate and do Conda, and you can go talk to the Python side, and it all works. And you're using those environments, but they're kept separate so we don't run into these weird bugs all the time. Next slide, and I think this is about the end. It's also offers users like all these extra things so they can do publishing. So they don't have to worry about installation of Tech Live, installation of all the packages, Jupyter Book, all that stuff. It's just like works out of the gate for them. So really reducing the barriers for staff. Next. Last slide. Next. This. And then the last thing was putting a lot of effort into documentation, not for the users. The users don't care what the image looks like, but developers, people who want to do what I did, who are developing Docker images, it's all in here, all the design decisions, and with the idea of future developers. Okay, if you want to do this, here's all the things I had to solve along the way. All right, thanks a lot, Julie.
Thank you so much, Eli. Fantastic. Yuvi, would you like me to continue sharing, or will you share your screen?
I am trying to share it. I think.
Great.
All right. There we
Take it
go.
away.
Okay. I think this works, right?
Looks
All
great.
right. Thank you, everyone. I'm gonna go through this real quick. So the overall idea I want to express is that users don't actually want to blow up cloud costs. So if we give them usable guardrails that help them understand and control their usage, then it automatically helps us as the people running and being responsible for this control cloud costs. And I want to emphasize the usable part of this because for a lot of it's like fish in water, right? Like I think for a lot of folks, their experience with these kind of controls come from HPC centers, which are not cost elastic, right? Like all of those, that money has already been spent. So reducing usage doesn't actually reduce cost necessarily for the admins, unlike on the cloud where like users reducing usage does in fact actually reduce our cost. So it's important to like think about this in like a different way. Because like roughly speaking, right, like this is, I think, to a first approximation true, usage is directly proportional to cloud cost. But it is important for it to be done in a way that is usable to the users. Like we are also, this is an open source ecosystem, right? Like I think because so many of us use so many closed source SaaS products all the time, it's always like, oh, well, this doesn't exist. And, that's it. There is nothing we can do, which is not true here at all, right? Like all of the tools that we are discussing and use are co-built and co-created by people like the people in this call, right? So over the last year or so, 2I2C, along with, the Jupyter ecosystem and like all of this, we have been trying to build more tools that help people control their usage. So I'm just going to go through a couple of them real quick. But the thing I want you to hear is that this is sort of in the early stages, and the people in this room are the people who are building all of this together, right? So if you want to sort of get in on the ground floor as such, please reach out and we can all collaborate through Openscapes and other places to make all of this happen. So the first is like per user home directory limits. This is being co-built with NASA Veda project and development seed. So, like the idea is that you don't want to have, like an infinitely elastic home directory that, grows forever as EFS does. But you also don't want to over provision, one disk per user, because that also gets really expensive. So we have found a really nice, we're working on this really nice project. This just rolled out to Openscapes hubs last night. And now everyone has like a home directory limit, right? So the idea here is that we have one disk that everyone can share, but then everyone has limits, right? Because in our experience, home directories are some of the scariest places where, like costs can explode, because you don't know you just downloaded 2 terabytes, right? Like, because you followed some tutorial somewhere that is for someone's laptop where you're like, yeah, download all this data from the cloud and then work on it. So this has been a great project. It's getting more and more production ready. So if this is something you're interested in, please reach out. And then the second is to restrict the server sizes that are available to users based on group membership. So you can have like this, right? Like if you look on the right, you see the drop down of various sizes available to users. And you can see that for a user, like with limited privileges, right? Like where they're just getting started. Maybe they're just here for a workshop. They don't need that much. Like we have a limited set, but then for more power users, you can see the environment is the same, but, like they just have access to more resources. And this can also, include GPUs and like whatever as needed in the future. And to add on to what Andy was showing earlier, like the other nice thing here is that we actually have access to how much of this that they actually use. So one, like wonderful future application is for us to like investigate, like, well, you got a 60 gig RAM server, but how much of that did you actually use, right? And then be able to help users make better choices. Because, honestly, these numbers are context-free, right? Like, how am I supposed to know what 7.4 gigs of RAM actually mean? So I think there is a lot of potential here in helping guide users in making choices so that they can accomplish the things that they want to do. But this is like a great start for where things can be. And then we are also starting to work on compute quotas on a per group basis. This is still being worked through. I'll share a link to the design document for this as well. And Earthscope, I think someone from Earthscope is also on this call, is hopefully we're going to probably work together on this and make this happen. So different groups of users can get like, all right, you get this much memory hours of compute, this month and whatnot. Just, because often cloud cost and usage is a power law, right? Like you have one user who's costing you like $2,000, whether they know it or not. And then like you have 100 people who are all costing you $20, right? So what you really want to do is to have like 5 people cost you $200 and then everyone else costs you $20, because you're serving more users for the same amount of cloud cost, or you're like, reducing the total amount you spend. So all of this sort of helps with that. And then the last bit, and this I think Andy also showed, is, like Prometheus, which is like an industry standard tool, is a great place for us to understand usage. And Grafana is a great place for us to, visualize that usage, right? And it's important that we integrate into, as open science people, it's important that we integrate into the wider open source ecosystem and reuse tools from there as much as possible. And then just build just enough of what we need, right? And Prometheus and Grafana, I think, are very critical tools here. And we have written a little bit of Python glue that talks to the AWS cost API and for cloud cost, and Prometheus for usage, and then is able to separate out, like how much each hub costs on a per day basis, right? And this is also the source of the data that Andy's using for like the reports that is being generated. But we are still very much scratching the surface, right? Because these tools are often built by open source people who don't really have, I want to say, often to a very rough approximation, a statistical background, right? Like, so while I find when I'm talking to people who do have a lot of like statistical experience, like, oh yeah, we can very easily take like this large chunk and reattribute it to multiple people if we know how much each person is using it, right? So we are in the very early days of doing this work. I think we'll hear more about it in this call as well. But this is a Python script that we've written that helps glue this together and provide reports in Grafana that you can explore and see like, oh, this hub is using this much. And eventually the hope is, we're able to say this group of users is using this much. And this, we already can say that for usage, right? But we can't say that for cost. And hopefully we will be able to do that. And the idea is that by having these on two sides, right? You have guardrails that prevent users from accidentally overdoing things. And then you have reporting things that allow admins insight. So then they can, as humans, go have conversations with these users to understand what it is they're trying to do, and then support them better, right? Like, I also culturally want us to move away from like the, like if you know what BOFH is, you know what it is, like where there's the like the metaphorical equivalent of being rapped on the knuckles because you did something you thought you shouldn't do on some cluster. I want us to culturally move away from that. And provide both, like guardrails and tools that admins can use for like, productive conversation with the users who we ultimately serve, right? So yeah, that's what I got. There is a lot of this cloud cost work that's happening right now. So if you have ideas, you have thoughts, please reach out to us. And hopefully we'll also have a blog post about this coming out soon. All right, thank you.
Awesome. Thanks so much, Yuvi. Great. And thanks for putting your questions in the chat and doc. We're going to have a great discussion afterwards. Alex, we are all set for you.
Great. I'll share my screen here.
Looks great.
All right. Great. So I'm Alex Lewandowski. I'm a research software engineer at the ASF DAC, the Alaska Satellite Facility. And so we are the SAR DAC. We distribute SAR data to the world. And so these are fairly large data sets. And in our JupyterHub, Open SAR Lab is designed around supporting users who are learning how to work with SAR data or developing algorithms to work with SAR data. And their resource requirements are often fairly large. And so I guess I should say that the name of my little portion here is, so what I'm looking at is how we can transfer these workflows from one hub to another. And the reason that we wanted to look into this is because JupyterHub funding has become increasingly unstable. More and more hubs are coming online, but then the support for those hubs are more and more tenuous. And so we envision the potential need for users to sometimes switch hubs on short notice. And so we want to make sure that the workflows that we're providing are able to be used in a variety of environments on different hubs. And we want to learn what we can do to make that those transitions easier. So what pitfalls will users face, and how can we as hub administrators ease those transitions, and then how can people working to create data recipes in Jupyter notebooks and Jupyter books, how can they develop their workflows in a way that also makes reduces the pain points of jumping from one hub to another. So for our little test here, we looked at moving one of Open SAR Lab's most commonly used workflows into the Openscapes hub and running it there. So here's just a quick little comparison of some of the features of each of these hubs that differ from each other. So of course, they're owned by and run by different organizations. They have different use cases. So OpenStarLab is very much SAR focused, whereas Openscapes was designed to support a variety of workflows in a variety of fields, often for short-run workshops. Storage is different. So in OpenStarLab, everybody gets 500 gigabytes of persistent EBS storage. In Openscapes, everybody has access to a home directory that's in EFS, and apparently now there are some guardrails on how much you can put there. So that's great to learn from Yuvi just now. And then there's also a persistent S3 bucket and a shared scratch bucket. And so in OpenStarLab, the expectation is that you have the storage. It's on demand. It's been paid for in advance. We don't really care if you fill it up or not. In Openscapes, it's more important to empty that directory because and to not leave data hanging around, because that is going to just accrue costs that would otherwise not be there. There are also both hubs offer a variety of server configurations for supporting different workflows, and then each offer control over your software environment, but in different ways. So in OpenStarLab, you have this persistent volume. You can build conda environments on this volume to support a variety of workflows. In Openscapes, there are ways to, there are some pre-made environments that may work for you, and if they don't, you can also point to a Docker image or a repo that's set up for Binder with a conda environment, and it will run that image or build that conda environment for you on the fly, and then start a server running that. So the workflow that I ran in both locations on both hubs is our most commonly used workflow. So this is a cumulative deformation insert time series with MintPy. So this allows you to take a stack of interferograms, a highly redundant stack of interferograms, and it performs an SBAS time series analysis that will show you the cumulative deformation over long periods of time, much longer than you would be able to extract from just a single interferogram over that same period. So I tried two different runs. I started small with just a half-year time series on a fairly small area of interest, and so this whole entire data set was 2.1 gigs, including, so right now we're not able to access this Sentinel data. We can't stream it or access it in place. So this is actually like downloading data to a user volume. And so in combination, the input and the output data was 2.1 gigabytes for that half-year time series. And then I also looked at a more reasonable sized time series that we might expect our users to work with more typically, which is in this case 28, almost 29 gigs. And so that's almost the full Sentinel-1 time series, about 8 years. And so it actually went very, very smoothly. Both hubs were provisioned with the correct with large enough server options to support this workflow. Both hubs sit in US West 2, so transferring that data to user volumes went very smoothly and efficiently. And because Openscapes uses repo to Docker, I was able to create an OpenStarLab image and just provide that to Openscapes and get a very and have a very similar experience to what I'm used to seeing in OpenStarLab, including all of our extra extensions that we install and things that really looked quite a bit like OpenStarLab to work in that in Openscapes. And there were a few minor issues which may or may not be related to the hub. In the first case, things were in MintPy. There is an option to use a local DAS cluster to speed up processing on a couple of the steps, and those failed. I didn't have time to look into and dig into the details of why exactly that failed. I suspect it's actually probably a dependency issue and probably isn't related to the hub at all. So that's probably just something I need to work with on the image, but it did just sort of point out, like, you jumping from one hub to another, you are going to run into some issues, and I did in this case. But so even though I had more CPU on the Openscapes hub than what I had available in the OpenStarLab hub, OpenStarLab ran a little bit faster because I was using both cores, whereas I was only using a single core in Openscapes. And then another interesting thing that popped up was just the missed markdown. Missed markdown is great. There are lots of additional features that you can use with missed markdown, and so we're starting to move some of our workflows over to missed, and some of them are not there yet. Some of them are still using vanilla markdown, and they don't necessarily always play nicely with each other depending on how you have the environment set up. And so those were two small issues that seem, minor and fairly easy to resolve. The main point was that I could run these workflows very efficiently in both locations. I guess the other main difference is that there would be an expectation in Openscapes that I then go and clean up my data. And if I just leave that sitting there, then it's going to cost more. Whereas those costs are sort of already built into OpenStarLab. And then Andy, did you want to talk about this plot at all? Showing
I can briefly talk about it. Yeah. So this is really, I found this really neat because so Alex went into the Openscapes hub and ran his workflow and said, Andy, this is when I was in there. Can you find me and see what I did and see what I used? And so Alex logged in using with a request for 3.7 CPUs and 7.4 gigabytes of RAM. So that was on a AWS R5 extra large instance. And so the sort of orangey browny line there is the amount of resources that Alex requested sort of over time. So this is about a 3-hour time period. And so the top plot there is the number of cores, CPU cores, and then the bottom plot is the amount of memory. And so you can see that he ran out of CPU, sort of like was CPU limited, but actually didn't end up using all of the memory that was allocated on that instance. And so this is just this is on the 28 gigabyte workflow, so with the full 8-year time series, and it's just a really good illustration of the challenges of finding the right size instance when you log into one of these things to do your thing. You can over allocate and you'd be spending money for a really big machine that you're not using, like Yuvi was talking about earlier, or you can allocate and just run into like problems where you run out of memory or it's just really, really slow and takes a long time. And so yeah, finding that that balance is tricky. But we can use these tools to help us learn from what we've been doing, to help us understand what these things are costing and then how we can do it the most efficiently. Yeah, I don't think, Alex, do you want to, is there anything in these lines any story that you want to talk about?
Thanks. Well, a little bit. I guess how this really brings up for me, how do we recommend, how do we provide the information to, and you touched on this as well, Yuvi, how do we provide this information to users so that they can pick the appropriate resources that they need and one, not waste money for the hub, but also, you don't want to put our users in a situation where they're just being continually frustrated, starting with the smallest possible option and working up and, running out of resources and shutting down the server and restarting. Like that could get very tiresome to try and work your way through and determine the minimal sized instance that you need. And also that's wasting money too, because you're having to redo this multiple times. So yeah, so I guess that's the big story that came out of these graphs for me was, how can we sort of dial in and provide more information to our users so that they're grabbing the appropriate resources. And then I also just had these general thoughts as I was going through this. Part of why this was so easy is because I had so much control over my environment in both hubs. Both in terms of server size options and also how I was setting up the software environments. While the path to setting up those environments was different for both hubs, it was very easy for me as a user to control that and get up and running quickly. Another thing that I've been thinking about just in general in terms of developing workflows is to make sure that they not only run in Hub, but they also provide a path for people to use locally. While we are all very excited about working in the cloud, some people will still want to work locally and may have a good reason to work locally on occasion. So, we should make that as easy as possible as well. And then also just thinking about the different ways that storage is handled on the two hubs. This is, this is one of the probably the most variable features across hubs is how storage is set up and handled and how much storage users have access to. So reducing storage requirements in the workflows is going to make those workflows more transferable across hubs. So for example, with S1, currently we're still in this with Sentinel-1, data, we're still in this mode of downloading the data, but that's changing very quickly. NISAR is coming. There will be in-place access for NISAR data, and more data sets are becoming easier to access in place. And so as that continues, maybe we can reduce our storage requirements, which will not only cost us less money, but make it easier to transfer these workflows. And then also, as we work out the kinks with NIST-MD and vanilla Markdown, that will also improve things as well.
Great.
I think that was I had.
Yeah, thank you so much, Alex. I wonder if will you go to the next slide too? Just, I know you all sort of wrap up the panel, had these kind of last take home thoughts, and then we'll move into some of the Q&A. I don't know who wants to unmute and share about this. But this has been super.
I can take a quick stab. So Alex touched on it there, that the storage is one of the biggest things that we need to sort of communicate to users and get users to use sort of like optimal workflows. The guardrails that Yuvi talked about are obviously a really critical part of the equation, and then the other part is the conceptual shifts that need to happen, so that we don't have like these huge amounts of data sitting at rest that costs money going forward. And I think that Alex touched on this too. There's two conceptual shifts there. I think one is starting to think about using object storage in S3 buckets for long-term storage of data that users do need to keep around. And the other one is, which is not on this slide, but is streaming data, doing sort of in-place subsetting, especially of of big remote sensing data, so that we're not downloading huge amounts in the first place because we don't need to do it. I think those are the sort of like the two biggest shifts in terms of storage. Yeah, I don't know, Yuvi, you might want to talk about the logging out, stopping your server. 2I2C does a lot of great work on making sure that we're not sort of leaving things chewing through resources.
Yeah, I mean, we've just contributed most of this upstream to Zero JupyterHub, and by default, if you leave it unused for an hour, it will just stop, because we don't expect it is reasonable for us to ask user to like shut things down. Like, you don't log out of your Gmail session when you leave anymore, right? So this mostly works. But if you find that it doesn't work, that's a bug. So please report it upstream, and then we'll find a way to like go and get that fixed. And this is more of the user-centric stuff, right? Like I don't want us to like yell at users for like, you didn't shut down your server. Let's fix our bugs so that they don't really need to. And if you do need specific cases where you want your server to keep running, like maybe you have a batch process running, there is a JupyterLab extension called Jupyter Keep Alive that we don't advertise very often because, we want things to shut down, but you are welcome to test that out and that will keep your server running. By default, you have to click a button every 24 hours to keep it running. Again, we're trying to balance cost and guardrails, but also allowing users to do the thing they want to do.
Great. Thank you all so much. Thank you. Like this has been a conversation and a really interesting chance to see what this collaboration looks like across open source infrastructure, federal government, science users. So thank you so much. There are questions that we have in the document on the bottom of page 7 from folks. Thank you to folks who've been helping respond to them as we go. There's some good questions about hubs in general, and I wonder if we want to focus on costs in this call. There's questions about controlling costs for data egress and long-term preservation. I don't know if any of the speakers could have a look at those questions and see if there's something to comment on from these questions. There's also a great question from Bruce Hawkins Brooke Hawkins, Brooke, about 2I2C and its relationship with the Openscapes and JupyterHub.
I wonder if Brooke wants to briefly unmute and say what she was thinking.
Sure, yeah. My name's Brooke. My pronouns are they, them. My question is not specifically related to cloud costs, but I am interested in hearing a little bit more. Yuvi, could you share about what 2I2C is and how it is related to and distinct from Openscapes and JupyterHub?
Sure. So 2I2C is a nonprofit. For me, the way I describe it is software as a service is how we all consume software in 2025. There is no reason that has to be VC-backed commercial startups. It is totally valid and open for us to bring the co-creation energy that we have for open source software into the software as a service world and create and be responsible for the tools that we build together. But we recognize that it takes a different kind of expertise, right? Like server administration, SRE, than either teaching open science or doing open science. So 2I2C as an organization was formed to do that kind of specialty work, right? So we run servers, we maintain servers, we contribute upstream to JupyterHub. JupyterHub is an open source project that, of course, has many stakeholders, and 2I2C is one of them. But many of us have been involved in JupyterHub for like a really long time. So I see us as sort of being in the middle, but not in like a rent extracting middleman kind of fashion, but sort of in the middle between JupyterHub, the open source tool, and communities like Openscapes, because communities like Openscapes have deep expertise in some things, and then they need other organizations that are similarly culturally structured that have deep expertise in sort of like running infrastructure, so that like Andy and Julie and all of those folks can focus on pedagogy and open science than on like Kubernetes versions, or on making sure that like this upstream contribution goes through so that multiple people can do that. So does that sort of answer your question?
Yeah, definitely. Thank you.
Thanks so much, Yuvi and Brooke. What about controlling costs for data egress? This is one question in the doc. For example, if data resides on one provider, but the user's infrastructure resides on another provider.
I can provide us one answer, which is don't. The idea is to bring your compute close to where your data is. And that is like, unfortunately right now, like the only real way to do that. I know that Europe is working on legislation around this because most of the reason that it costs so much is artificial. That's not how much it actually costs the providers. So maybe in 10 years, we'll have a different answer, but right now, I would say the answer is move your compute close to where the data is. This also has performance like improvements, but fundamentally right now, I think it's like really cost related. I'll also share a link in the chat and in the doc about a document that we've written that helps you think about the various things that cost in the cloud, and it has a section on data egress and how to think about it as well.
And Yuvi, correct me if I'm wrong, but the Openscapes hubs are US West 2 only, right? So we can't.
And they are US West 2 because NASA and AWS have an agreement that puts NASA data only in US West 2.
Yeah, awesome.
Great. I wonder if we just have time for one more question. I see Sam's question about long-term preservation and access, and if there's a way to project costs in the 5 or 10-year timeframes. Does anybody have thoughts on that?
Assuming they're talking about storage costs, Sam, I mean, I think you can. So object storage is the cheapest long-term storage solution. So AWS S3 on an AWS, and there are different sort of levels of archival storage that are cheaper, sort of like the more difficult it is to access. And so maybe you know all this, but already, and I'm talking to the converted, but it would be able to, you could project that cost out. I mean, assuming a constant pricing from Amazon, which may or may not be reasonable to assume, but yeah, I think you could project that out. I'm not sure, Sam, if that is what you're after, though.
Great. Well,
Just
go ahead, Yuvi.
quickly add on to that, I would also encourage looking at things like OSN or source co-op because I do think it's important to have multiple options for long-term archival that are also distinct from the commercial cloud providers where we have more control, more access, but also like peace of mind to be able to like recognize like, all right, like how do we sustain this so that it is actually still here in 10 years?
Great. Thank you all. I'm sorry we didn't get a chance to answer all your questions live, but they are in the doc and we will come back to them. We will be writing a blog post summary, and we'll be posting the recording on YouTube and sharing that out both through the blog post when it comes, but also through the events page shortly. Thank you so much to all of our speakers and collaborators and friends for being here. And there's a few announcements at the bottom of the doc, but we want to let you go bottom of the hour. So thank you so much, everyone, and have a great rest of Earth Day. Bye.
Bye. Thank you.
Thanks very much.
Thank you for organizing.